So in this session, we are going to discuss about single phase half bridge and full bridge voltage source inverter. So here, this circuit is half bridge voltage source inverter, and this circuit is the full bridge voltage source inverter, and these two circuits are built by the SPDT switches, that is single pole double throw switches. These two circuits are the basic circuits of the half bridge and full bridge voltage source inverter. Now let us analyze the half bridge inverter. So here it will be let me draw the output voltage V0. Here the Vs by 2 is the one source and the Vs by 2 is the other source, the second source. And here Va0 is the pole voltage. Va0 equal to pole voltage. Va0 is called as pole voltage. And here V0 is output voltage. So V0 here it will be the Va0. So V0 here it will be the Va0. So from here, so if I close the switch to the, so this is the pole and these two are the throws, right? These two are the throws. So if I close the switch to the S1, what happens if I close switch to the S1? For example, if switch S1 is closed, in between the period of the T to T by 0 to T by 2. Let this time period is T, and so let this as the total time T, and it is a T by 2. So if 0 to T by 2, if I close the switch, S1 is in on condition. If I close the switch to the position to the S1, so what happens? This positive of the Vs by 2 is connected to here, S1 terminal, and so positive is connected and O is connected to the negative. So that VAO will become the Vs by 2. VAO will become the Vs by 2. So VAO will be Vs by 2. So for example, in the same situation, if I close the switch to the S2, what happens? So this is an SPDT switch, that is single pole double throw switch. So we can close to either S1 or S2. So if I close to the S1, it will be the Vs by 2. If I close to the S2, what happens? This negative, so if I close to the S2 and this negative is connected to the S2 terminal, so S2 will be the negative. So A is connected to the negative, so that it will be the minus Vs by 2. Minus Vs by 2. So it will be the minus Vs by 2. Minus Vs by 2. So here the switch S2 is in the on condition. From T by 2 to T, the switch S2 is in on condition. From 0 to T by 2, the switch S1 is in on condition. So this is how we will get the alternating voltage. So alternating voltage, that is square wave at the output voltage. So similarly, let us look at full bridge voltage source inverter. So here we are taking the two SPDT switches. For implementing the voltage source, full bridge voltage source inverter, we are taking the two SPDT switches. For example, if I close the S1 and S4, if I close the S1 and S2, what happens? So if I close the S1 and S2, in this case, if I close the S1 and S2, so the output voltage will be, so here it will be the plus and here it will be the negative. So A is connected to the plus and B is connected to the negative. So let VAB or V0, so both are equal, VAB equal to V0. So if I find the VAB, so if the S1 and S2 is closed for the period of T by 2, so what happens? S1 and S2 are closed. S1 is, the switch is closed to the S1 and here the switch is closed to the S2. So what happens? The current flows in this direction. So A to B, the current flows in this direction and the output voltage will become the plus Vs. So it will be the Vs. So now if I close the switches, so here S1 and S2, I close the switches into the S1 and S2 position. Now if I close the switches into the S3 and S4 position, so what happens if I close the switches to the S3 and S4 position? If I close the switches to the S3 and S4 position, S3 and S4, so let me represent with other color. So if I close the switch S3 and S4, so if I close the switches S3 and S4, what happens? So the positive terminal is connected to the B and the negative terminal is connected to the A. Negative terminal is connected to the A. So it will be the VAB is negative and it will be the minus Vs. So from T by 2 to T, so it will be the minus Vs. Minus Vs. minus Vs. Here the switches are closed in the positions of S3 and S4. For example, in pulse width modulation techniques, so we can observe this condition also. So that is, if I close the position into the S1 and S3, what happens? If I close the position into the S1 and S3, so this load will get short circuited. If I close the position in S1 and S3, what happens? So this load will get the short circuited. So output voltage will become the 0. So if I close the S2 and S4, so what happens? The output voltage will become the 0. So there is no possibility of closing the S1 and S4 at the same time. If I close the S1 and S4, what happens? So if I close the S1 and S4, the source will get short circuit. So that S1 and S4 are the complementary switches. S1 and S4 are the complementary switches. So that is S1 is the complement of S4. That is, when S4 is in on condition, S1 should be off. When S1 should be in on condition, S4 should be off. So here S2 and S3 position also the complementary positions. So they should not be closed at the same time, because if you close at the same time, it will short circuit the source. Now let us realize this switch SPDT. Now let us realize this switch. So how to realize the switch? So first we need to draw the graph so that we can realize the switch. That is, let me take I on y-axis, V on the voltage of the switch on the x-axis. So here the load is AC load, so that load should carry the current in both the direction. In positive half cycle it is in one direction, in the negative half cycle it is in the opposite direction. So here, if the switch is closer to the S1 position, the switch also should carry the current in both the direction. It depends on load. Actually, it depends on load. So it should able to carry the current in the both the direction. It must able to carry the current in the both the directions. And voltage blocking capability. To find the voltage blocking capability, so what we have to do? So I need to close the switch to the S1 position. To find the voltage blocking capability of S1P, so VS1P I need to find. So the VS1P should be equal to, if I close the switch to the S2, so S1P in the open circuit, right? It is in the open circuit. So when it is an open circuit, so it is closer to the S2, the negative terminal is connected to the P. So P is negative, S1 is positive. So the voltage across VS1P will be the positive. Voltage across S1P is the positive. So that we need to replace the switch in such a way that it should carry the current in both the directions and it should block the positive voltage. The switch should be, so now the switch should be like this. So we know that IGBT can block the voltage, IGBT can block the positive voltage, and it can, IGBT with anti-parallel diode, IGBT can conduct in this direction, diode will conduct in the opposite direction. So that we can replace one switch with the, so like this, VS1P. Similarly, S2P also we can replace with the switch with bidirectional switch. So I will represent the switch will be like this. So we can replace with the thyristor with anti-parallel diode, or the IGBT with the anti-parallel diode, or the MOSFET with the anti-parallel diode. So it needs to be there should be an anti-parallel diode, because it is operating in the AC loads. Now, so let us realize the switch here. So how we can realize the switch? So we can realize the switch here. It will be, so here also the current flowing in the both the directions. The current flows in both the directions because of AC load. In the positive half cycle it is in one direction. In the negative half cycle it is in opposite direction. So that if the switch is closer to the S1 position, so when you apply these, so what happens? So the current should carry the current in both the direction. The switch must able to carry the current in the both the direction. And we will find the blocking voltage. Let me find the blocking voltage here. So how we can find the blocking voltage? So we can find the blocking voltage S1P. Let me find the S1P here. VS1P. So Vs1p, the polarity of Vs1p. So to find the Vs1p, let me close the switch to the S4. Let me close to the switch to the S4, and this switch will be in the open circuit condition. Open circuit condition. So during that time, S1 will connect to the positive of the source. Here it is closer to the S4. So S4 is connected to the P, and P is the negative. So if I apply the voltage, it will be the positive and negative. So it should block the positive voltage, and so it should carry the current in both the direction. Here also the switch should be replaced in such a way that the switch should be like this. The switch should be like this. So this is how we realize the switches from the SPDT. Now we will draw the circuit diagram with an electronic switches, that is IGBT with anti-parallel diode, or we can replace the switch with the anti-parallel diode. So now let us draw the circuits of the half bridge and full bridge inverter. So this is the circuit of half bridge inverter, and here it is the circuits of the full bridge inverter. Here it is the circuits of the full bridge inverter. So here VA naught, in this case VA naught equal to V naught, so which is equal to output voltage. So let me assume this current, so it will be the load. So let me assume the current of I naught will be like this. Current of I naught will be like this. Now, so here also VAB is an output voltage. VAB is an output voltage which is equal to V naught, and let me assume current will be in this direction. So current will be in this direction. Now let us analyze these two circuits first. So after that we will apply for the different loads, that is R load, pure inductive load, RL load, as well as the RLC load. So here this switch S1 will carry the current in this direction, and diode will carry the current in the opposite direction, right? Diode will carry the current in the opposite direction. Now let us find the possible condition. Let us analyze the half bridge inverter here. So let me find the possible conditions of the switches. So we can close the S1, right? We can close the S1. So we can close the S2. This is one possible condition. So there may be possibility of closing the D1, and there may be the possibility of the D2. So there may be the possibility of the D2 also. So there may be the possibility of D2 also. Now let us find the V0 and VA0 and I0. VA0 and I0. So if you can get this concept in the half bridge inverter, you can apply for the full bridge inverter. So please listen carefully at half bridge inverter so that you can try for the full bridge inverter here. So here listen carefully. So let me find the VA0. When S1 is in on condition, so what about VA0? Let me close the switch of VA0. Let me close the switch of VA0. So I should close the switch in this direction. So the current flows in this direction. So right, the current flows in this direction, so that the switch will allow the current in this direction from top to bottoms. So the current will be I0 assumed direction and actual current direction both are same, so that I0 will be the positive. I0 is positive. So what about VA0? VA0 equal to, so here it will be the plus minus Vs by 2, and here it will be the plus minus Vs by 2. So here VA0 equal to, so the positive terminal is connected to the A and O is connected to the negative. So that VA0 will be the so Vs by 2. VA0 will be the Vs by 2. And when S2 is in on condition, now let me close the S2. So what happens we will see. Let me close the S2. So if I close the S2, what happens? The current direction will be, so in this direction. The current direction will be in this direction. So the current is flowing from the O to A, but we are assumed that initial current is in the A to O. So that it will be the current will be the negative. So if I find the output voltage will be the minus Vs by 2. So that is VA0 will be the minus Vs by 2. Now let us close the D1. So if I close the D1, so what happens if I close the D1? The current flows in this direction, right? The current flows in this direction, that is O to A. So the current will be the negative. So the output voltage will be, same, because positive is connected to the A and negative is connected to the O. So that output voltage will be the Vs by 2. So now if I close the D2, what happens if I close the D2? So if I close the D2, so now let me close the D2. So if I close the D2 here, so the current direction will be in this direction. So current flows in this direction. So it will be in this direction. So the current is flowing from the A to O. So assumed direction and actual current direction both are same. In this case, assumed direction and actual current direction both are same. So what happens? So it will be the positive and output voltage will be the minus Vs by 2. So these are the, if you can analyze these conditions, so it will be easier for you to analyze for the different loads, that is R load, resistive load, inductive load, RL load and RLC loads. So here, so one more thing we need to observe here. So here, what happens if I close the S1 and S2? If I close the S1 and S2 in this case, so what happens? It will short circuit the load. So if I close the S1 and S2, what happens? It is parallel to the load, it will short circuit the load, so it can damage the source as well as the switches. So it will be the not possible condition. S1 and S2 should not be on at same time. So that S1 is the complement of S2. That is, when S1 is in on condition, S2 should be in the off condition. So when S1 is in off condition, S2 should be in the on condition. So S1 and S2 here are the complementary switches. They should not be on at the same time. So now we are able to, now you have the basic concept of half bridge inverter. With that basic concept, let us find for the full bridge inverter. So now let me write the possible combinations: S1, S2, S3, S4, D1, D2 and D3 and D4. So now let us analyze these conditions. So here V0 and I0. So with this basic concept, if you can understand the half bridge inverter, so you can write the expression for the V0, that is V0 equal to VAB, and it will be the I0. So I0 will be the, so we are assuming that I0 is flowing from the A to B. So when S1 and S2 is in on condition, what happens when S1 and S2 is in on condition? So when S1, S2 is in on condition, so the output voltage is equal to Vs. When S1, S2 is in on condition, the output voltage is equal to Vs, because positive is connected to the A and negative is connected to the B. So Vs. So what about the current? So the current direction will be in this direction. So assumed current direction and both are same, it will be the positive. So when S3, S4 is in on condition, what happens when S3, S4 is in on condition? So when S3, S4 is in on condition, output voltage should be equal to minus Vs. So, and the current direction will be, so current direction also be negative. So when D1, D2 is in on condition, what happens when D1 and D2 is in on condition? So close the D1 and D2 and check. So here close the D1 and D2 and check the D1 and D2. So if I close the D1 and D2, so the current direction will be B to A, but the output voltage will be same. So Vs and the current will be negative. So when D3, D4 are closed, what happens when D3, D4 are closed? When D3 and D4 are closed, so the current direction is same as assumed direction, but the output voltage is minus. So here also there are pole voltages VA0 and VB0. VA0 and VB0 are the pole voltages. VA0 and VB0 are called as pole voltages. If you know the VA0 and VB0, you can find the VAB also. That is, V0 will be equal to VA naught minus VB naught. So which is equal to VAB. VAB. So for example, when S1 is an on condition, so what about VA naught? So VA naught and VB naught. We will find the VA naught and VB naught. So we'll find the pole voltages also. So when S1 is an on condition, so what about VA naught? So S1 is an on condition, VA naught will be equal to, so understand here, don't get confused, understand here. So there is nothing here. So it is as simple as, so when S1 is an on condition, VA naught equal to Vs by 2. So observe here, VA naught equal to, so Vs by 2. Positive is connected to the A and O is connected to the negative. So S1 is an on, so VA naught equal to Vs by 2. So when S4 is on, so what happens? When S4 is on, so when S4 is on, so VA naught equal to, when S4 is on, so let me draw the S4. So let me close the S4. When S4 is on, so what happens? So the negative of the Vs by 2 is connected to the A and positive is connected to the O. So VA naught will becomes the, S4 is on, VA naught will becomes the minus Vs by 2. So when S3 is on, so what happened when S3 is on? So when S3 is on, so this is the parallel. So S3 is on, what happens? VB naught should be equal to Vs by 2. So VB naught is Vs by 2. So when S2 is on, VB naught equal to minus Vs by 2. So this is how we can calculate the pole voltages also. So from the pole voltages also we can find the output voltage. For example, if S1 and S2 is closed, so what about VA naught, VAB? So VA naught equal to Vs by 2, VB naught equal to minus Vs by 2. So when S1 and S2 is closed, so VA naught equal to Vs by 2 and VB naught equal to minus Vs by 2. So it will be the VA naught minus VB naught, so it will be the Vs. So you will get the same value. So from the pole voltages also we can determine the output voltage. So this is how we will calculate the pole voltages. When S1 is on, so VA naught equal to Vs by 2. When S4 is on, minus Vs by 2. S3 is on, VB naught equal to Vs by 2. S2 is on, VB naught equal to minus Vs by 2. So VB naught equal to minus Vs by 2. So now we got the pole voltages and line voltages. So here also we have determined the pole voltage and line voltage. So here S1 and S4 are the complementary switches, S3 and S2 are the complementary switches. So now let us look at, so on this analysis, now if you know this analysis, so up to here it is the basic analysis, it should be in your mind, so that if you have these concepts in your mind, so it is easy to apply this concept for the different loads, that is R load, RL load, RL load and the RLC load. So we will see the R load. Now we will see the R load. Now we will see the R load here. So in the R load, so resistive load for half bridge inverter, resistive load is applied to the half bridge inverter, and when it is applied to the full bridge inverter, so this side will take the full bridge inverter. So in the half bridge inverter we have the switches S1 and S2, and S1 and S2 are the complementary switches. That is, when S1 is in on condition, S2 should be in off condition. When S2 is in on condition, so S1 should be in the off condition. So now let me draw the firing pulses. So let me take the switch as here in this condition. Let me replace the switch with the thyristor with the anti-parallel diode. So now let me draw the gate pulse for S1. So from here to here. So again, that is, let me represent the time periods 0, T by 2, T and 3T by 2. So here, so I will give the gate pulses in between these two instants, that is 0 to t by 2 and t to 3t by 2. Now let me draw the gate pulse for the S2 here. So here, gate pulse for the S2 will be like this. Gate pulse for the S2 will be like this. So, and it is the complementary position, that is when S1 is in on condition, S2 should be in the off condition. So when S1 is in off condition, in this period it will be in the off condition, so that S2 should be in the on condition. So the gate pulses will be like this. Now let me draw the V0 waveform here. V0 waveform here. So we know that when S1 is on, so VA naught equal to, that is pole voltage equal to V naught. So VA naught should be equal to Vs by 2. So it should be equal to Vs by 2. So and this magnitude should be equal to Vs by 2. And VA naught equal to Vs by 2. So from this table, when S2 is on, so here it will be the minus Vs by 2. Minus Vs by 2. So minus Vs by 2. So here in this case, if I draw the load current, how the load current would be? So the load current will be the V0 by R. So here I0 equal to V0 by R. So that is, the load current will be like this. Load current will be like this. So with the reduced magnitude, and it will be equal to V0 by R. And this magnitude will be V0 by R. So that is Vs by 2R. So and this magnitude will be, so Vs by 2. Vs by 2 and minus Vs by 2. So if I apply the Fourier series for this, so for the output voltage, so we have derived the Fourier series expression for the square wave. So that is V0 equal to sigma n equal to 135 to infinity 4 into, so here the magnitude will be, amplitude will be the Vs by 2. So that is 4 into Vs by 2, 4 into Vs by 2 divided by n pi into sin n omega t. Sin n omega t. So which is equal to 2 Vs by n pi into sin n omega t. Sin n omega t. 2 Vs by n pi into sin n omega t. So what about the Fourier series expression for I0? So I can write the Fourier series expression for I0 also. So I0 equal to V0 by R, that is sigma n equal to 135 to infinity. So it will be the 2 Vs by n pi into R into sin n omega t. Sin n omega t. So here we have written the, so V0 and I0 Fourier series expression for the half bridge inverter. So for the half bridge inverter, if you have these analyses, you can draw the output voltage and output current for the full bridge inverter also. So for example, as we know that, so let me mark the time instant 0, t by 2, right, t and 3t by 2. So from 0 to t by 2, so here we are closing the S1 and S2, right? So we are giving the triggering pulse for the S1, S2, and in this condition we are giving the triggering pulse for the S3 and S4. Again it will be the S1 and S2. So for these topologies, for this condition, different switching condition, let me draw the pole voltages. First let me draw the pole voltages. As we know that, so when S1 is a on condition, so it will be the VAB and it will be the I0, right? So when S1 is a on condition, VA not equal to Vs by 2, VA naught is equal to Vs by 2, and it will be the minus Vs by 2 when S4 is an on condition. So it will be like this. So here let me draw the VB naught, that is pole voltage, the voltage between the VB, that is B potent B and B point and O point, that is VBO. So VB minus VO, so which is equal to, when S1 is an on condition, so when S2 is an on condition, what happens? So it will be the minus Vs by 2. So it will be the minus Vs by 2, and when S3 is an, when S4 is an on, S3 is an on condition, it will be the plus Vs by 2. So minus Vs by 2 and plus Vs by 2, and this magnitude would be the Vs by 2. So now let me draw the VAB. So what about VAB? VAB is nothing but VA minus VB. VA minus VB. So we know that when S1 S2 is an on condition, it will be the VS. Similarly, if I find the VA naught minus VB naught, that is VS by 2 minus of minus VS by 2, I will get the VS here. So it will be the VS. So again it will be the minus VS. So it will be the minus VS. So it will be the VS again. Now we have got the output voltage waveform VAB or V naught. So let me draw the I naught in this. So I naught with the reduced magnitude, right? I naught will be like this. That is Vs by R. So that is V naught by I naught equal to V naught by R. I naught equal to V naught by R. So now here also let me write the Fourier series expression. So you know the Fourier series expression for this we have derived in the basics of the power electronics. So from this V naught equal to sigma n equal to 135 to infinity. So 4 Vs by n pi into sin n omega t. Sin n omega t. So I naught equal to, so 4 sigma n equal to 135 to infinity. 135 to infinity. So it will be the 4 Vs by n pi r into sin n omega t. Sin n omega t. So to solve any problem regarding the resistive load, these Fourier series expressions as well as these waveforms are sufficient for the resistive load. So and these tables should be needed, and here these waveforms are sufficient. So if you observe here, the conduction angle is limited to the conduction angle will be the, so here it will be the 0 to pi. So this instant is, if t is 2 pi and this instant will be the pi. So now let us find the different parameters from these waveforms as well as the V naught and I naught waveform. So V naught and I naught waveform. So let me find the parameters, different parameters from this. So here the different parameters are nothing but, so for example, let me find the total harmonic distortion here. Total harmonic distortion here. So here the total harmonic distortion will be, let me find the total harmonic distortion. The first parameter is the total harmonic distortion. So here I will find for the half bridge inverter, you try to find for the full bridge inverter. So parallelly you also prepare, and it will be the exercise for you. So you also prepare for the full bridge voltage source inverter. So first I will do for the half bridge inverter. So be participate in this context so that you will get the, easy conceptual transfer. So here for the total harmonic distortion equal to, we know that it will be the equal to 1 by G square minus 1, where G is the distortion factor. G equal to Vs1 divided by Vs. So V naught 1 divided by V naught. So that is fundamental output voltage RMS value divided by fundamental output voltage RMS. So total output voltage RMS value. Now let me find the G value from this. G equal to, so we know that V naught 1 equal to 2 Vs by pi divided by root 2, right? So divided by, so 2 Vs by pi divided by root 2 divided by, so V naught RMS for the square waveform will be the Vs by 2. So Vs by 2. So from this, so if I find the G value, how the G value will be? So the G value will be the, so and Vs will get cancelled. So it will be the 2 root 2 divided by pi. 2 root 2 divided by pi. So which is equal to 0.9. So THD will be, if I find the THD, it will be the 48.34%. So if I substitute the G value in the THD expression, I will get the 48.34%. Now try to find the THD value in the full bridge inverter. So THD here it is equal to THD equal to, So again here the formula will be the same, which is equal to 1 by G square minus 1. G equal to fundamental RMS voltage divided by output voltage. So here the fundamental RMS voltage will be the 4 Vs by pi divided by root 2, so divided by Vs. So here the output RMS value will be the Vs. So again we are getting the 2 root 2 divided by pi, 2 root 2 divided by pi. So if I find the THD, so that is 0.9, if I find the THD, so it will be the 48.34%. In percentage it will be the 48.34%. So whether it is a full bridge inverter or half bridge inverter, the THD value is same. Now let me find the maximum value of the fundamental current. So what about the maximum value of the fundamental current? So the maximum value of the fundamental will be the I01 max, right? So which is equal to, here it will be the 2 VDC by N pi into R. So here N is where N equal to 1, so that 2 VDC by pi into R. So here I01 max will be the, so the value will be the 4 VDC by N pi. So 4 VDC by pi is the 4 VDC by pi into R. It will be the I01 maximum. So now let me find the RMS fundamental current. So RMS fundamental current would be the I01 RMS equal to, so maximum value divided by root 2. So that is maximum value by divided by root 2. I will get the root 2 into VDC divided by pi into R. And here I01 RMS would be root 2 into VDC divided by 2 root 2 into VDC divided by pi into R, because 4 VDC by pi R divided by root 2, I0 maximum by root 2. So now let us find the average and RMS value of the switching current. Average and RMS value of the switching current. Here the switch is conducting for the pi period. Here the switch is conducting for the pi period. So if you observe here, so S1 is conducting for the pi period. S1 is conducting for the pi period. So similarly, so let me draw the switching currents first. To understand this, let me draw the switching currents here. So let me draw the switching currents. So if I draw the switching currents, here the switching current S1 is flowing from 0 to pi, right? 0 to pi. S1 is flowing from 0 to pi. So now let me draw the switching current so that you can understand easily. So let me draw the switch current. So when the switch current is flowing, so let me draw the switch current so that it is easy to write the expression. So in both the cases, so here switch S1, if I draw the IS1, so how it will be? So IS1 flows from here to here, 0 to pi. Again it will start at 2 pi. So that is 0 to t by 2. So here it will be the t. 0 to t by t. It is conducting for 0 to t by t, and the maximum value of the current will be the I0 maximum. So I0 maximum will be the, so V0 divided by 2R, that is Vs by 2R. I0 maximum, which is equal to Vs by 2R in this case. So in this case it will be like this again. So if I draw the IS1, it will be like this. So for t by 2 period, so on this peak will be the Vs by R. So right. So this is the IS1, that is switch current. So let me call it as a IT1. So here also let me call it as a IT1. So now if I find the average value IT1, so IT average will be we need to find the IT average. I naught maximum into T by 2 divided by T. So which is equal to I naught maximum into T by 2 divided by T, which is equal to I naught maximum divided by 2. So where I naught maximum equal to Vs by 2R in this case. So now let me find the IT RMS. IT RMS. So what about IT RMS? So IT RMS would be the I naught maximum into maximum square into T by 2 divided by T, which is equal to I naught maximum divided by root 2. I naught maximum divided by root 2. So which is equal to RMS value. Which is equal to RMS value. So here, so it is I naught max. So I naught max. Here also we'll get the same expression. So because the switch S1 is T1 is conducting, so for the period of T by 2, and we are getting the same waveform. Here also we are getting the same waveforms, but the difference is here I naught max is, in this case I naught max will be, so IT1 max will be I naught max, so which is equal to Vs by R. So here it will be the Vs by 2R. So this is only the difference here. Now let us find average and RMS value of the fundamental switch current. Fundamental switch current. How we can find the fundamental switch current? So here we can find the fundamental switch current will be like this. So please understand at this level only, so that you can understand easily for the remaining loads. So here the switch is conducting for the 0 to pi, right? 0 to pi or 0 to T by 2. So 0 to T by 2. So if I draw the fundamental current will be the sinusoidal nature. So it will be like this. And this peak value will be the I naught 1 maximum. I naught 1 max. I naught 1 max. Now, if I want to find the average value of the fundamental switch current, so it will be the, let it be the IT. So IT1, I need to find here IT1 average value. IT1 average value. How I can find the IT1 average value? So here no need to by heart any formula, just remember the procedure, just remember the concept. No need to by heart, no need to mug up the any formula here. So IT1 average equal to, so 1 by 2 pi into integration of 0 to pi. So I naught 1 maximum into sin omega t. I naught 1 max into sin omega t d omega t. So similarly IT1 RMS equal to, so we can find the RMS value from this 1 by 2 pi into integration of 0 to pi. So I naught 1 max whole square into sin square omega t d omega t. Sin square omega t into d omega t whole power 1 by 2. This is the RMS value. So this formula is same for the both half bridge and full bridge inverter. So half bridge and full bridge inverter, and this formula will be the same, and we will find the average value of the thyristor current and as well as the average value of the RMS value. The average value of the fundamental switch current, RMS and average values of the fundamental switch current. So next we will find the power delivered to the load due to fundamental current. So this is as simple as P01. So P01 equal to V01 RMS. So V01 RMS into I01 RMS, that is fundamental RMS current, into cos pi 1. In this case cos pi 1 equal to 1 because pi 1 equal to 0. So we'll get the formula as P01 equal to V01 RMS into I01 RMS. So I01 RMS. So this is important. So we know that V01 RMS will be the, so we can find from the Fourier series expression. I01 RMS also we can find from the Fourier series expression. So that power delivered to the load we can find from the Fourier series expression. Now let us find the fundamental power delivered by the source. fundamental power delivered by the each source. If you can find for one source, so if you multiply by 2, you will get the total power. So here fundamental power delivered by the each source will be equal to, so PS, let me call it as a PS, source power. So which is equal to VDC by 2, one source will be the VDC by 2 into IS average value. That is source current, so IS1 average value, source 1 average value. So that is fundamental source current average value into VDC by 2, you will get the, for one source, if you multiply by the 2, you will get the total power delivered by the sources, total power delivered by the sources. So here also same, for each source it will be the, so power will be the VDC by 2 into IS1 average, IS1 average, IS1 average. So this is how we will find the different parameters, and we have forget the two more things, that is conduction period of the diode and conduction period of the thyristor. So in case of resistive load, the conduction period of the diode is 0 and the conduction period of the switch will be the pi. So in case of resistive load, there is no need of the flyback diodes or the freewheeling diode or an anti-parallel diode. So here 2 switches are sufficient. So in case of full bridge inverter, 4 switches are sufficient. So now let us analyze half bridge and full bridge inverter with the pure inductance. So now let us analyze the operation and analysis of half bridge and full bridge inverter with the pure inductive load. So if the pure inductive load is connected, so at the load of the half bridge and full bridge inverter, so let me draw the output voltage and output current waveform. So here whatever be the load, that is R load, pure inductive load, or which may be the combination of resistance and inductance RL load, or it may be the RLC load. So whatever be the load, in case of voltage source inverter, the voltage waveform nature will not change. So it is constant. Voltage waveform nature would be constant. So if I draw the output voltage, here, so in case of half bridge inverter, it will be like this. The voltage nature will be like this. Voltage nature will be like this. So the voltage nature will not change. So it will be like this. So this magnitude will be the Vs by 2. So but in this case, so let me draw the I0 waveform. So here, so as we know that VL equal to LdI by dt. So LdI by dt. So here VL equal to V0 and L into di0 by dt, right? So from this I0 equal to integration of VL by, that is V0 by L into dt. So because it is a pure inductance, the inductive current lags the voltage by 90 degrees. So here let me represent the time period, let it be the T by 2, we can also represent with the pi T, so we can also represent with the 2 pi, and it will be the Tt by 2. So if the current is lags by 90 degrees in case of pure inductance, and if I integrate the square wave, that is unit step, I will get the ramp wave or triangular waveform. So the waveform nature should be like this. So it should be like this, and it lags the voltage by 90 degrees, that is T by 4. It lags the voltage by 90 degrees, that is T by 4. So and the output voltage is equal to, output current can be drawn like this. Output current can be drawn like this. Output current can be drawn like this. Now this is the output current. Now here we need to mark the devices. How we can mark the devices in this period? So Now let me mark the devices here so that you try to mark for the full bridge inverter. So understand the concept in half bridge inverter. So you should apply the same concept for the full bridge inverter because these two circuits are acts as a similar nature. So very with the small differences. So you can find the differences also here if you study like this. So here, if you observe here, in this portion of period that is 0 to t by 4, what happens? So 0 to t by 4, so output voltage is positive and the current is negative here. Current is negative here. So when output voltage is positive, current is negative. When output voltage is positive and the current is negative, so the device should conduct will be the D1. So here the D1 should conduct. The D1 should be conduct. So now in the second case, that is T by 4 to T by 2, T by 4 to T by 2, which device has to be conduct? So now you can tell the device. So in this period, from this period to this period, so from this period to this period, so we can, so output voltage is positive here. So output voltage is positive here and output current also be positive. Output current also be positive. So now which device will conduct? So output voltage is positive and output current is positive. So the device will conduct is S1. So here S1 is the device which will conduct. Now here output voltage is negative, output current is positive. So the device is output voltage is negative minus Vs by 2, output current is positive. So the device will be the D2. So here it will be the S2. Both are negative. So again the same cycle repeating here, it will be the D1 and it will be the S1. So this is how we will mark the devices here. Now let me find the maximum value of the load current. Maximum value of the load current. So let me derive the maximum value of the load current. How we can determine the maximum value of the load current? So here let me mark it as a minus Imax and this is the plus Imax. Let me mark it as a plus Imax. Now, so as we know that VL equal to LdI by dt, so DI equal to VL by L into dt, right? VL by L into dt. So if I take the period from here to here, so from here to here, 0 to t by 2, so the current is varying from the minus Imax to the Imax. Minus Imax to the Imax. And the time period will be the 0 to t by 2. 0 to t by 2. So now, so if I apply the integration like this, so how I will get? So Imax to minus Imax to Imax, if I integrate this one, I will get the 2 Imax, right? So 2 Imax and it will be the VL by L into t by 2. Right? VL by L into t by 2. So that Imax will be so VL by L into VL by 2L, so VL by 4L into T. So 1 by T, so VL by 4L into T. So Imax equal to VL by 4L into T or VL by 4LF. So we can also represent as a VL by 4L into F. So this is the maximum value of the current where T equal to 1 by F. Where T equal to 1 by F. So now try to find for the full bridge inverter. Try to find for the full bridge inverter. So as we know that, so let me draw the output voltage. So now you are able to draw the output voltage because the nature of the output voltage will not change by depending on the load. So whether it is R load, RL load, RLC load, the output voltage waveform nature will be the same. So now let me draw the output voltage will be like this. First let me draw the output voltage. So the output voltage will be like this. 0, T by 2, T and 3T by 2, right? So now let me draw the I naught value. So here how to draw the I naught? So as we know that the inductive current in the triangle nature, so it will be like this, and it lags the supply voltage, that is output voltage, by 90 degrees. 90 degrees, that is T by 4. So it will be like this. The current will be like this. So the current will be like this. So again it is varying from the minus I max to the I max. Minus I max to the I max. So now let me mark the devices here. Now you are able to mark the devices from the table. So try to mark the devices from these waveforms. So here, and this is the question asked for the different competitive exams. So you try to mark the devices. You try to mark the devices. So from this table. So from this table you try to mark the devices. So here, so output voltage is positive, current is negative, right? So voltage is positive, current is negative means D1, D2 will conduct. So in this period, the devices will conduct is D1 and D2. Let me mark it with the other color, D1 and D2. So again from this period to this period. So voltage is positive, current is positive. So Vs and Vs. So the devices will be the S1 and S2. S1 and S2. So and here from here to here. So the devices will be, so voltage is negative, current is positive. So the device will be the D3 and D4. So again, so from here to here, so voltage is negative, current is negative. So that it will be the S3 and S4. S3 and S4. So again here same cycle repeats, that is D1, D2, S1 and S2. So this is how we will mark the devices. Now let us find the maximum value of the load current, I max. Let us find the I max. So how I can find the I max? So I max will be the here. So it di integration of di equal to integration of VL by L into dt. So here if I take the limits from 0 to t by 2, 0 to t by 2, how it will be? 0 to t by 2. If I take the limits from 0 to t by 2, so di will changing from the minus I max to I max, minus I max to I max, and it will be the, so VL by, so here it will be the, so VL equal to VS, right? VS by 2. So here VL equal to VS by 2. In this case VL equal to VS by 2. So that here I max will be the VS by 8 into LF, because here VL equal to V0, so V0 equal to Vs by 2. So let me find here also. So 2 I max equal to Vs by L into T by 2. Vs by L into T by 2. Vs by L into T by 2. So here VL equal to Vs, so it will be the Vs by L into T by 2. So I max will be here. So Vs by 4 into LF. 4 into LF. So this is an important expression. Here Vs by 8 into LF. So here it will be the Vs by 4 into LF. Because here VL equal to Vs. So here VL equal to Vs by 2. And this is the Vs and this is the Vs by 2. So now we got the maximum value of the output current. Maximum value of the output current. So let us find the remaining parameters. So what about remaining parameters? So the Fourier series expression also be same for this. So the Fourier series expression also be same. So let me find the Fourier series expression for this to find the THD. So here V naught equal to, as we know that sigma n equal to 135 to infinity, 2 Vs by n pi into sine n omega t, and I naught would be, so let me write the I naught also. So I naught would be So what about I naught? The Fourier series expression for I naught will be sigma n equal to 135 to infinity 2 Vs by n pi into n omega L. So here is the inductance, so it will be the n omega L. We need to divide it by the n omega L because inductance is depends on frequency. Inductance will be depends on frequency. When it is fundamental, it will be the omega L. When it is third harmonic, it will be the 3 times of omega L. So it will be the n omega L into n pi. So that is n square into omega L pi. N square into omega L pi into sine n omega t minus pi is where pi is the pi by 2. So pi by 2 minus pi by 2. So here the THD will be same because the output voltage expression will be the same. THD will calculate the as same as resistive load. So here also THD will be the 48.34%. So because the voltage THD will be the same because the voltage nature will not be changing here. Now let me write the expression here. V naught equal to here sigma n equal to 135 to infinity. So it will be the 4 Vs by n pi into sine n omega t. Sine n omega t. So I naught will be sigma n equal to 135 to infinity 4 Vs by n square into omega L pi into sine n omega t minus pi by 2. Minus pi by 2. So now let us find the maximum fundamental current. So what about maximum fundamental current? So here the maximum fundamental current will be the I01 max. I01 max. So what about I01 max here? So the I01 max equal to, so the value of I01 max will be, so it will be the 2 Vs by n square. So that is n square equal to 1 because it is a fundamental. So it will be the omega L into pi. Omega L into pi. So here I01 max will be the 4 Vs by omega L into pi. So fundamental RMS current will be the I01 RMS will be I01 max divided by root 2. So here I01 RMS will be I01 max divided by root 2. So here don't remember as a formula. So don't remember as the equation. You just remember the basic equation that is sufficient to solve the problems. So let us find the average and RMS value of the switching current. So here in this case, the conduction period of the diode is same as conduction period of the thyristor. So which is equal to each device will conduct for the period of pi by 2. So each device will conduct a period of the pi by 2, that is or t by 4. So pi by 2. Now let us draw the IT waveform. So how to draw the IT waveform? So that is switch waveform. The switch current will be like this. So let me draw the switch current. Here. First, for that, let me draw the output current. The output current would be like this, right? So in this period, when will be the IT1 will conduct? So IT1 is conducting from here to here. From here to here. So IT1 will be like this. So from 0 to 2 pi. So it is conducting from the pi by 2 to pi. So this is IT1. Similarly, and this maximum will be the I0 max. So which is equal to Vs by 8 LF. So similarly, if I draw the diode current. So ID1, diode current ID1, if I draw, it will be like this. So it is conducting in this period. So in the total time period, the diode D1 will conducting in this period. So which will be the minus I naught max. Minus I naught max. So ID will be like this. Minus I naught max. So if I find the average values, so average value of the thyristor current is same as, so average value of the thyristor current will be same as average value of the diode current. Average value of the ID, average value of the diode current. So here also we will get the same thing. So here also we will get the same thing. So either full bridge or a half bridge, so we'll get the same waveform. So but I naught max value only the difference, but the waveforms are similar. So how to find the average value? So which is equal to half into, so area will be the half into I naught max into, right, I naught max into, so pi by 2 to pi, that is T by 4 to, so here it will be the T by 4, so or pi by 2, we can make it as a pi by 2 also. So in the period of the 2 pi, in the period of the 2 pi, so it is conducting for the period of, so it is conducting for the period of pi by 2, so pi by 2, so it will be the T by 4, it is conducting for the period of T by 4 in the total time T, so in the total time T, so we can make it as a T in the total time T. So it will be the half into I max T and T will get cancelled. So 1 by 8 into I max, I naught max. So 1 by 8 into I naught max. So for this, so we can find the RMS value also. So for the square wave, for the triangle waveform, so the area of the square of the waveform will be the, so the area of the square of the waveform will be the a square tau by 3 divided by 2 pi. So in the basics we have discussed, so how to find the RMS value of the triangle waveform. So how to find the RMS value of the triangle wave. So RMS value will be IT RMS or ID RMS will be equal to ID RMS equal to, so what about the IT RMS and ID RMS values? So the area of the triangle, that is area of the square waveform, that is a square, so that is I naught max whole square, so into T by 4 for the period of T by 4 divided by 3, so divided by, so time period will be the total time period will be the T, so whole power 1 by 2, so which is equal to I naught max divided by I naught max into T and T will get cancelled, so which is the 1 by 2 root 3, I naught max divided by 2 into root 3. So this is where we will get the IT RMS value. So IT RMS value. So this way, this one we get the this one. So for the triangle waveform, we have found the RMS value in the basics of the power electronics. So in the switching theory, we have derived the RMS values and we have derived the shortcut also. Please refer the shortcut to find the RMS value in the basics of the power electronics. Now let us find average and RMS value of the fundamental switching current. So what about the average and RMS value of the switching current? So the switching current would be like this. The switching current will be like this. So here the switching current will be like this. So let me draw the switching current waveform. So the switching current waveform will be like this. So let me draw the switching current waveform so that you can understand easily. So the switching current waveform will be like this. So it will be like this. If I draw the fundamental current also be like this in this position. So it will be the pi by 2, right? It will be the pi by 2. So for the average value of the RMS value of the switch current, the switch is conducting in between the period of pi by 2 to pi. Pi by 2 to pi. So So the switch is conducting in period of the pi by 2 to pi. So if I draw the switch current in this, so if I draw the switch current, how it will be? The switch current will be like this. The switch current will be like this. Fundamental switching current will be like this. So because it is conducting in the period of this one. So how we can find this? So I switch fundamental IT1, so which is equal to 1 by 2 pi into integration of pi by 2 to pi, integration of pi by 2 to pi, so 90 to 180 degrees, so into I naught 1 max, I naught 1 max, so this is the maximum value of I naught 1, right? So I naught 1 max, so I naught 1 max into sine n omega t minus pi by 2 into d omega t. So from this expression we can find the switching current, fundamental switch current of the in the pure inductive load. So similarly IT1 RMS would be so 1 by 2 pi into pi by 2 to pi I naught 1 max whole square into sine n omega t minus pi by 2 whole square into d omega t whole power 1 by 2 whole power 1 by 2. So while solving the problem, we will see the how to find the fundamental switch current also we will see. So power delivered to the load due to fundamental current, So it will be equal to V naught square. So P naught 1 equal to V naught 1 RMS into I naught 1 RMS into cos pi 1. So where pi 1 is the fundamental displacement angle. So which is the angle between the V naught 1 and I naught 1. So in this case pi 1 equal to pi by 2. So cos 90 equal to 0. So active power is power delivered due to the fundamental current would be the 0. So again here the power delivered by the each source, so which is equal to Vs by 2 into Is average. So here also Ps equal to Vs by 2 into Is average. So if I find the fundamental reactive power, so Q naught 1 will be the V naught 1 RMS into I naught 1 RMS into sine pi 1. So where pi 1 equal to pi by 2, so it will be the 1. So which is the Q naught 1 and P naught 1. So this is how we will calculate the different parameters. Regarding the pure inductive load. Now we will see analysis of the half bridge and full bridge inverter. So with the RL load. So now let us analyze operation and analysis of half bridge and full bridge inverter for the RL load. So which is the combination of resistance and inductance here. So here, so let V naught is output voltage. Let me represent V naught here and let me draw the I naught here. Here also let me represent V naught and let me represent the I naught. So as we discussed earlier, so in case of voltage source inverter, the output voltage waveform nature will not change by depending on load. So that is, if the load is resistive, even the load is resistive RL load or RLC load, so or the pure inductive load, the output voltage waveform nature will be the same as R load. So that in case of R load, we have drawn the output voltage that is 0 to T by 2, it will be the Vs by 2. 0 to T by 2, it will be the Vs by 2, and T by 2 to T, it will be the minus Vs by 2. Again, it will be the plus Vs by 2. So the output voltage waveform nature would be the similar. So here also, if I draw the output voltage, it will be the Vs, and here T by 2 to T, So it will be the minus Vs. Minus Vs. So now we have drawn the output voltage waveform for the both the cases. Both the cases. So now let us find or let us draw the output current, and let us find the nature of the output current, and we'll find the maximum value of the output current also. So let us look at this one. So in case of R load, so let me analyze for the full bridge inverter. For the full bridge inverter, so for the full bridge voltage source inverter, I will analyze here. So from that we can find the half bridge inverter. So here from 0 to T by 2, as we know that from 0 to T by 2, 0 T less than T by 2, V naught equal to Vs, right? So in case of full bridge inverter. So from T by 2 to T, so V naught equal to minus Vs. So let me represent in a circuit. So here the load is RL load is R and L load is RL load. So here the load is RL load, and the sources are, so one is a DC source. So one more thing is, it will be like this. So it will be like this, right? So it will be the Vs, and here it will be the minus Vs. At T by 2, at T equal T by 2, so it is switched to the minus Vs, right? So here it will be the V naught. So here it will be the V naught. The circuit we can represent like this. The circuit we can represent like this. So initially up to T by 2, so it is connected to the Vs. So that is 0 to T less than T by 2. So V naught is Vs, that is I into R plus L into di by dt equal to Vs. So if I simplify this one, so it is a combination of steady state response as well as transient response. The steady state response would be the Vs by R, and the transient response I will represent with the A into e power minus t by tau. A into e power minus t by 2. So let this equation number will be the 1. So equation number 1 will be the 1. So let me take I of 0 as I minimum. I of 0 as I minimum. So at t equals 0, it has a minimum current. Let me assume that it has a minimum current, that is I minimum. So if I find I of t, so I of t, from this I of t equal to, so Vs by R plus A into e power 0 is equal to I minimum. So from this A equal to I minimum minus Vs by R. I minimum minus Vs by R. So if I substitute in this, so I will get the A value. So I will get the A value. So I will get the I of t expression. So we are getting the A equal to I minimum minus Vs by R. So now at 0 to T less than T by 2 we have seen. So now we'll see T by 2 to T. So T by 2 to T, so if I close this switch to the minus Vs source, so that is minus Vs source, so that is here. Now it will be the I of t should be equal to minus Vs by R plus B into e power minus of t minus t by 2 divided by tau, right? So this is the second equation. Now let me find for the current for the second equation. So the current for the second equation would be, so I of t, let me represent I of t by 2 equal to I max. So if I substitute I of t by 2 here, when t equal t by 2, so it will become B equal to I max plus Vs by R. So 0 to t by 2 to t, the equation would be like this, and 0 to t by 2, the equation would be like this. So here it will be the exponential term. So from this, so we know that, let me draw the output current. So output current is in the exponential nature. So as we know that in case of R load, the current lags the voltage by pi. So let me represent the angle pi here. So if I draw the current in the exponential manner, so it will be like this. So it will be like this. So during steady state, what happens? So let me represent this as a I minimum. So let me represent this as a I maximum. I maximum. So here also, let me represent this as a I minimum. So here also current waveform nature would be the same. So and let me represent this as a I maximum. So the current will be the same, and this is the pi. This is the pi. So now at IL of t, that is I naught of t equal to, again it is I minimum. So I naught of 0 is equal to I naught of t. So from this I naught of t is equal to I naught of 0 is equal to I naught of t, right? So because of symmetrical nature, so and which is equal to I minimum, I naught of t by 2, so equal to I maximum, I maximum. So if I substitute these two in the equation number, so equation number 1, so equation number 1, so what is the equation number 1? So if I substitute this relation in the equation number 1, so Vs by R, so otherwise I will substitute the t by 2 here. So t by 2 in the equation number 1. So IL of t by 2 is the common thing. So I naught of t by 2 equal to, so if I substitute in the above equation, that is 0 to t by 2, so which is equal to Vs by R plus A into e power minus t by 2 equal to, so minus Vs by R. If I substitute in the equation number 2, it will be the minus E by R, Vs by R plus B into e power 0. So from this we'll get the one equation. So the next will be the, when I substitute the IL of t by 2 equal to, so IL of 0 equal to IL of t by 2. So IL of t. So IL of t. If I substitute this equation, so equal to I minimum, as we know that both are equal. So if I substitute IL of 0 in the first equation, it will be the, so IL of 0 equal to, so IL of 0 equal to Vs by R plus A into e power 0. So IL of t equal to, so in this case it will be the Vs by R minus Vs by R plus B into e power minus t by 2. E power minus t by 2 divided by tau. So which is equal to, so both are equal. So let me call it as a fourth equation. So let me call it as a third equation. So if you compare the 3 and 4 equations, so we'll get the A equal to minus B. So A equal to minus B. And here we'll get the symmetry. To get the symmetry, that is I max should be equal to I minimum. So I max equal to minus I minimum. So if you find the I max, so you no need to remember this expression. So just remember that, no need to remember all these derivation. So just remember this expression, that is I max equal to minus I minimum equal to Vs by R into 1 minus e power minus t by 2 tau divided by 1 minus e power minus t by 2 tau divided by, so it will be the minus t power 1 plus e power minus t by 2 tau. So this is the expression for the I max. So we'll get the I max for the full bridge inverter like this. So this is for full bridge inverter. So for half bridge inverter, so half bridge voltage source inverter, the only change will be the, so I max would be I minus I minimum. So the derivation would be same, and it will be the Vs by 2R. So here Vs by 2R. So we need to replace Vs with the Vs by 2. 1 minus e power minus capital T by tau divided by 1 plus e power minus t by 2 tau. So this is how we will find the I max and I minimum. If you find the I max and I minimum, you can find the, so So we can find the I of t also. We can find the I of t also. Now let us find here. Now let us find here. So here, find the conduction period of the different devices. So in pure inductive load also we have determined the conduction period of the different devices. So now let me find the conduction of the different devices also here. So from 0 to pi, if you observe from 0 to pi, so which device is conducting here? So voltage is positive and current is negative. So voltage is positive and current is negative means, so this one, so diode D1 will be in the conduction state. So from pi to t by 2, so the device will be conduction state, both are positive, so that S1. So here voltage is negative, current is positive. In between the, from here to here. So here it will be the D2, the device will be the D2. So here the device will be the D2. And here the device will be the S2. So again here the device will be the, again it will be the repeative cycle. So it will be the D1 and here it will be the S1. Right? So here it will be the S1. Now we have determined the conduction period of the different devices, like pure inductive load. So here so if you observe here, so from 0 to pi, voltage is positive, current is negative. So voltage is positive, current is negative. So the conducting devices are, so voltage is positive, current is negative means the conducting devices are D1, D2. So here both are positive, the conducting devices are S1, S2. So here voltage is negative, current is positive. Voltage is negative, current is positive. So voltage is negative, current is positive. So it will be the D3, D4. D3, D4. So here voltage and current both are negative, it will be the S3, S4. S3, S4. Similarly, so it is a cycle, after T it will be the D1, D2 and it will be the S1, S2. So now we have found the different parameters. Now let us find different parameters for the half bridge inverter and full bridge inverter. So let us find the half bridge inverter and full bridge inverter different parameters. Let us find here. So let us find here. Let us find the parameters for the half bridge inverter and full bridge inverter. So at the same time. So now let me write the Fourier series expression. So output voltage does not change, because so that Fourier series expression for the output voltage would be, so Fourier series expression for the output voltage will be 2 Vs sigma n equal to 135 to infinity. So it will be the 2 Vs by n pi into sine n omega t. So here V0 will be V0 equal to sigma n equal to 135 to infinity. So it will be the 4 Vs by n pi into sine n omega t. Right? Sine n omega t. So now let us write the I0 expression. So I0 expression. So I0 will be the V0 by Z, that is sigma n equal to 135 to infinity. So it will be the 2 Vs by n pi divided by Zn. N pi divided by Zn into sine n omega t, where Zn equal to square n omega t minus pi n, n omega t minus pi n. So it will be the n omega t minus pi n, n omega t minus pi n. So n omega t minus, so it will be the n omega t minus pi n. Sine, because current lags the voltage. So n omega t minus pi n. Sine n omega t minus pi n. So now let us represent Zn. So what is Zn? So Zn equal to square root of r square plus. So for nth harmonic, the frequency will be the n omega. So it will be the n omega L into whole square. So now let us find the pi n. So pi n equal to tan inverse of, so it is an impedance angle. So it will be the n omega L divided by r, tan inverse of XL by r. So here also, so let me write the I0 and V0 expression. So I0, Fourier series expression for the I0 will be sigma n equal to 135 to infinity. 4Vs by n pi into Zn into sin n omega t minus pi n. So current lagging, right? So here also Zn is same, which is equal to square root of r square plus n omega l square, n omega l whole square, and pi n would be tan inverse of omega n omega l divided by r. So the fundamental displacement factor. So the fundamental displacement factor would be same, that is cos pi 1. So pi 1 is nothing but square root of r square plus omega l square. We need to substitute. So here also same fundamental displacement factor. And now let us find the I naught 1 maximum. So the maximum value of the I naught 1 will be, so it will be the 2 Vs by pi into Z1. 2 Vs by pi into Z1. So here if I find the I naught 1 maximum, that is maximum value of the fundamental load current would be, so it will be the, so 4 Vs by pi into Z1, where Z1 equal to square root of r square plus omega l square. So now we got the I naught max. Now let us find I naught 1 RMS. So I naught 1 RMS. Now let us find the I naught 1 RMS. Let us find I naught 1 RMS. So you can find the I naught 1 RMS if you know the I naught 1 maximum. So I naught 1 RMS equal to, I naught 1 RMS equal to, so 2 Vs by pi into Zn divided by root 2. So that is root 2 Vs by root 2 into Vs by pi into Zn. So here let me find the I naught 1 RMS. That is RMS value of the fundamental load current. So which is equal to 4 Vs by pi into Zn into root 2. So which is equal to 2 root 2 Vs by pi into Zn. So Z1. So here we need to take the Z1. So that is square root of r square plus omega l square. So now we got the I naught 1. So let me find the conduction period of the diode. So here the conduction period of the each diode will be the from 0 to pi. So it will be the pi. Conduction period will be the of the diode will be the pi, and conduction period of the thyristor will be the pi minus pi. Thyristor is conducting from the pi to, so phi to pi. So if I want to find the, fundamental diode current, so fundamental diode current ID1 average or ID1 RMS would be, so ID1 RMS equal to, so the fundamental diode current will be, so it will be the average value, so we can take from the limits as 1 by 2 pi. So it is conducting in between the 0 to pi, and the current will be the, so fundamental current will be the I naught 1 max into sine omega t minus pi into d omega t. So we need to square this one, and it should be the under root. So similarly, IT1 RMS value. So the RMS value of the thyristor current will be, fundamental thyristor current will be the, so 1 by 2 pi into, so integration of, we need to take the limits from the pi to pi, because the current would be like this. So the current will be like this, the load current is like this. So from here to here the diode is conducting, so from here to here switches are conducting. So let me call it as a T1. So if it is thyristor 1, so let me call it as a switch 1. So current will be like this. Diode is conducting from here to here. So thyristor is conducting from here to here. So it will be the, again I naught 1 max whole square I0 max whole square into sine square into omega t minus pi d omega t whole power 1 by 2. So here also you'll get the same expressions, because to finding here it will be the same expression, but I0 max. So I0 max value only the changing, but the procedure for finding both of these is same. So voltage, so fundamental power delivered here, it will be the V01 RMS into I01 RMS into cos pi 1 into cos pi 1. So here also you'll get the same expression. Here also you'll get the same expression. So this is how we'll calculate for the RL load. So when we're solving the problems, and if you observe at summary, so all these things are placed at one place so that it will be easy for you. So now let us analyze the half bridge and full bridge inverter for the RLC load. So now let us analyze operation and analysis of the half bridge and full bridge inverter with RLC load, that is resistance, inductance and capacitance. Now let us analyze with the RLC load with the series combination of resistance and inductance and capacitance. So whatever be the load, whether it is the R load, RL load or RLC load, the output voltage is waveform nature will be the same in case of voltage source inverter. So that the output voltage will be like this. So in the period of T by 2, so let me mark the periods as T by 2, T and 3T by 2. So let it be the time period T. So here it will be like this. So in case of half bridge inverter, so the voltage polarities will be like this. So it will be the Vs by 2 and it is the minus Vs by 2. So it is the minus Vs by 2. So now let us draw the I0 here. So in case of RLC load, we should consider two cases. So let me take the first case is Xc is greater than XL. So Xc is greater than XL. So what happens if Xc is greater than XL? So if you observe here, so during 0 to T by 2, how it will be 0 to T by 2, if I take from the period of 0 to T by 2, so VDC by 2 equal to I into R plus L into di by dt plus 1 by C into integration of I dt, right? So this already we have analyzed in the load commutation, that is class A commutation. Please refer that class A commutation for this equation. So we'll get the I as VDC, that is, let me represent as a Vs. So Vs by omega L, the 2 omega L into e power minus delta t into sine omega t. So where omega equal to 1 by LC minus R by 2L whole square under root. So under root. So delta equal to R by 2L. So if Xc is greater than XL, so it is operating in leading power factor. So it is operating in leading power factor, as well as load commutation is possible. Load commutation is possible. So for this equation, please refer the load commutation, that is class A commutation. So please refer the class A commutation in the DC to DC converter lecture. So now, so let me draw the I0 value. So how I can draw the I0 here? So I0 should be the sinusoidal, and it is operating at leading power factor, so I0 leads the V0 by an angle phi. So I0 should start from here, so it should lead the angle like this. So I0 should be like this, right? So the I0 will be like this here. So at this stage, you are able to mark the devices. Now you are able to mark the devices. So it is pi, right? It is pi. So here, So up to here it will be the pi minus pi, pi minus pi. So if t by 2 is pi and t is 2 pi, so let this be omega t and it is 3 pi. If I make it as 3 pi, so how it will be? So it will be like this, and so here voltage is positive and current is also positive. So that conducting device will be S1. So here voltage is positive, current is negative, so that here the conducting device will be the D1. So here voltage and current both are negative, so that current conducting device will be the S2. Conducting device will be the S2. So here it will be the D2. So again both are positive, S1. So from here to here, so here it will be the D1. So here it will be the D1. Now, so we have drawn for the XC is greater than XL. XC is greater than XL. So let me draw for the XL is greater than XC. What happens if XL is greater than XC? If XL is greater than XC, so XL is greater than XC, so the current waveform should lead the current waveform should lag the output voltage. So it should lag the output voltage like this. So it should lag the output voltage like this. So for this, so from here to here voltage is positive and current is negative. So voltage is positive, current is negative, so that the device will conduct in the D1. So here both are positive, S1. So here current and voltage is negative, current is positive, so that it will be the D2 in this portion. So it will be the S2, again D1 and S1. So here if you observe here, so the S1 should turn off here. At this instant S1 should turn off and D2 should be on. But the current is not getting 0. So here if you observe, the current is naturally 0 by the commutation, by the load commutation. So here it is not getting the 0, so that in case of XL is greater than C, so at this instant the forced commutation is required. Forced commutation is required. So forced commutation is required. So when XC is greater than XL, so it is commutated by the load commutation. So when XL is greater than XC, so here, so the forced commutation is required. So if you observe here, so after turn off S1, so that circuit turn off time is always greater than the device turn off time. Circuit turn off time is always greater than the device turn off time for the proper commutation. So that the circuit turn off time is nothing but, so here we are applying the reverse voltage across the device, that is S1. So we know that S1 will be like this. So at this instant, that is pi minus pi. So what happens? The diode is get into the conduction state. So that when it is get into the conduction state, the reverse voltage will apply across the device. The reverse voltage will apply across the device. So when diode is on, the reverse voltage will apply across the device, and this period is called as circuit turn off time. So this period is called as the circuit turn off time. So omega Tc, and this period will be the pi. The circuit turn off time of the device will be the, so omega Tc equal to pi. So omega Tc equal to pi. So and pi Tc equal to pi by omega. So omega Tc equal to pi, and Tc is equal to pi by, so Tc is equal to pi by omega. So pi by omega. From this we can find the circuit turn off time. So it will be the pi by omega. Similarly, let us draw the, so now you are able to draw the full bridge inverter also, because these two are the same, only the devices, conducting devices will change, and the magnitude of the amplitude of the output voltage will change. So here the amplitude of output voltage would be like this. So the output voltage waveform will not change. So it is Vs and it is minus Vs. So it is the minus Vs. So let it be the T. So now let me take the condition as Xc is greater than XL. So what happens if Xc is greater than XL? So here the current will be, Vs by omega L into e power minus delta t into sine omega t. And omega t equal to pi, the current will become 0. So it will be like this. So it will be like this. So because it is here Xc is greater than XL, so what happens in this condition, the current should lead the voltage. So current should lead the voltage by pi angle. So here the current will be like this. So here the current will be like this, same as here. So the current is same, but the conducting devices here, so now you can mark the conducting devices, guys. So here up to here both are positive, so that S1 S2 are in the conducting devices. So here voltage is positive, current is negative, so that D1 and D2 are the conducting devices. So here, so again here both are negative, so that S3 S4 are the conducting devices. So here the conducting devices are D3 and D4. The conducting devices are D3 and D4. So here also load commutation is possible because the S1 and S2 will turn off here. So when the load current equal to 0, when the load current is naturally becomes 0 by the load components, by the nature of the load, so that it will be in the load commutated inverters. So again here it will be the S1 S2, and here the cycle will repeat, it will be the D1 and D2. So now this is for Xc is greater than XL. For example, if I draw the so it is for the leading power factor. So now let me draw for the XL is greater than Xc. XL is greater than Xc. So if XL is greater than Xc, it should lag the output voltage, so that it will start from here, and the output current will be like this. So at this instant, voltage is positive, current is negative, so that D1, D2 are conducting devices. So at this instant, so both are positive, so that S1, S2. So at this instant, D3 and D4. So at this instant, S3, S4. Again, D1, D2 here. So again, S1, S2 here. So this is how we can draw the output voltage for the two different conditions. So here also, so the circuit turn off time, that is when S1 is off. So when S1 is off, what happens? There should be some reverse voltage is applied across the device by turn on the D1 and D2. So here also, it is a switch with anti-parallel diode S1 and D1. So what happens at this instant, that is pi minus pi to pi. So what happens at this instant? So at this instant, the diode is getting on, so that diode forward voltage drop will reverse bias the switch here, so that after turn off the switch also, it is maintaining some reverse voltage, so that it is called as circuit turn off time. So omega Tc equal to here pi, and the circuit turn off time is equal to so Tc, which is equal to pi by omega. So pi by omega. In both cases, it will be the pi by omega. So now let us find different parameters. So as we have did in RL load, the same analysis here also we have to do. So let me find the different parameters here. So first I will find the Fourier series expression for the half bridge inverter. So the Fourier series expression for V0 of omega t, V0 of t equal to sigma n equal to 135 to infinity 2 Vs by n pi into sin n omega t, right? Sin n omega t. V0 RMS equal to Vs by 2. So similarly here V0 of t equal to sigma n equal to 135 to infinity, so 4 Vs by n pi into sin n omega t, So here V0 RMS, total V0 RMS should be equal to Vs, and I0 of t equal to, so what about I0 of t? So I0 of t equal to V0 by Z, that is sigma n equal to 135 to infinity, so 2 Vs by n pi into Zn into sine n omega t minus pi n. So minus pi n. Sine n omega t minus pi n. So sine n omega t minus pi n. So we have to represent like this. Sine n omega t minus or plus pi n. Plus or minus pi n. So it depends on the load. It depends on the load. So plus for the leading power factor. So plus for the leading. So leading means XC is greater than XL. Minus is for lagging. So XL is greater than XC. So here also the same thing. So I naught of t will be, so I naught of t will be 4 Vs by n pi into Zn into sine n omega t plus or minus pi n. So for Xc is greater than XL. So what about Zn value? So they both have the same values of Zn. So Zn will be the same. So Zn equal to, so what about Zn? So Zn equal to sine Zn equal to square root of r square plus omega L minus 1 by n omega L minus 1 by n omega C whole square. So when XL is greater than XQ. So the same Zn we can represent as r square plus, so 1 by n omega C minus n omega L whole square. So when Xc is greater than, so when Xc is greater than XL. Xc is greater than XL. So this is how we will find the Fourier series expressions. From this we can find the I01 max, I0 and everything. So let us find the, so here let us find the thyristor RMS current and thyristor average current. So the fundamental thyristor average current will be the fundamental thyristor average current. How the fundamental thyristor average current here? So the fundamental thyristor average current will be the, so IT1 average will be, so 1 by 2 pi into, so the switch current will be flowing from the, so here pi to, so pi to pi, so phi to pi, so it will be the I01 max into sine n omega t plus or minus pi into d omega t. So IT RMS would be, so 1 by 2 pi, IT1 RMS should be 1 by 2 pi, pi to pi, so I01 max whole square into sine square n omega t plus or minus pi. So in both cases it will be the same, but I01 max will be the different. So I01 max will be the different. So this is under whole root. So both cases we will find the same analysis. And the conduction angle for the diode will be the pi. Conduction angle of the thyristor will be the pi minus pi. So here pi can be evaluated from, so pi n equal to tan inverse of, so tan inverse of XL by R, that is omega L minus n omega L by 1 n omega C divided by R. So plus or minus, here plus or minus. So minus. So minus is for XL is greater than XC. So plus is for, sorry, so it will be the different. So when XL is greater than XC, so we should get the negative. So we should get the negative here. So here it will be the negative. It is positive, and here it will, we need to take the reverse polarity for the, so n by omega c. So here it will be the negative. So we need to take the this polarity when XC is greater than XL. So we got the pi n also. So the output power would be, how the output power will be calculated? So P01 equal to V01 RMS into I01 RMS. The fundamental output power transfer to the load will be the into cos pi 1 into cos pi 1. So this is all about analysis of the half bridge and full bridge inverter. Now, so without all these analysis, let us have a generalized formulas so that the most of the problems on the formula based in this, so that we will find the generalized approach to find the different parameters in the half bridge and full bridge inverter in the summary. So let us summarize the whole thing. So let me summarize whole thing. So the summary will be, so let me summarize the whole thing. So the generalized analysis, if I make the generalized thing, so the Fourier series, whatever be the load, so the Fourier series expression for the output voltage will be, so V naught equal to sigma n equal to 135 to infinity Vn into sin n omega t. Vn into sin n omega t. So where Vn for the half bridge inverter, for the half bridge voltage source inverter, so Vn equal to 2 VDC by n pi. For the full bridge voltage source inverter, Vn equal to 4 VDC by n pi. 4 VDC by n pi. So similarly, let me write the output current expression. So output current expression would be, so I naught equal to sigma n equal to 135 to infinity. So I naught n into sin n omega t, so minus pi n, sin n omega t minus pi n. So here in this case for the R load, so the pi n is equal to 0. So for the R load, so the pi n we need to replace with the 0. So for the RL load, so pi n equal to tan inverse of n omega L divided by R. So for the RLC load, so pi n equal to, so tan inverse of omega L minus 1 by omega C, n omega L minus 1 by n omega C divided by R. So if XC is greater than, XL is greater than XQ. XL is greater than XC, that is inductive reactance is greater than the capacitive reactance. So this formula will be applicable. This is the same formula and this formula will be applicable for the different things. So here I naught n will be the, so let me find the I naught n here. So I naught n would be, so how to determine the I naught n? So I naught n is Vn divided by Zn. So here the Zn equal to R for the resistive load, for R load. So Zn equal to square root of R square plus n omega L square for the inductive load. So that is for RL load. So for L load, so it would be the n omega L. So here for L load, pi n equal to 90 degrees. So here for Zn equal to square root of, so it is n omega L, square root of R square plus n omega L minus 1 by n omega C whole square. So when XC is greater than XL is greater than XC. When XL is greater than XC, so this formula will be applicable. So these two formulas are sufficient. If you remember these two things, so these are sufficient. You can write any expression. So you can write any expression for this. So now let us find the remaining expressions also. So RMS value of the fundamental switching current. So the average value and RMS value you will see here. Otherwise average and RMS value you will see here. So the average and RMS value. So for the average and RMS value, so the average value of the fundamental switching current will be, so 1 by 2 pi into pi to pi to pi into I naught 1 into sine n omega t minus pi into d omega t, pi 1 into d omega t. So this is the average value of the switching current, that is IT1 average. IT1 average. So this is the average value of the fundamental switching current. So from this expression we can find, for example, if it is resistive load, so pi 1 equal to 0, we should make the pi 1 equal to 0, and I naught 1 we can find from the, so there, so I naught n, when you substitute 1, you will get the I naught 1. Similarly, IT1 RMS would be, so it is also same formula, it will be the 1 by 2 pi into integration of pi to pi I naught 1 into I naught 1 square, that is maximum value, this is the maximum value, I naught 1 maximum whole square into sine omega t minus pi 1 whole square into d omega t whole power 1 by 2, whole power 1 by 2. So this is how we can calculate for this. So the average value of the fundamental, so diode current. So in case of resistive load, so diode current will be the 0, right? The average value of the diode current will be ID1 average equal to, so we should take the 0 to pi. So here I naught 1 maximum value, that is peak value, I naught 1 maximum value into sine n omega t, so it will be the sine omega t minus pi 1 into d omega t. So from this formula we can find. So if in case of resistive load, so 0 to 0, phi equal to 0, so that it will be the, so phi equal to 0 in case of resistive load, it will be the 0 for the resistive load. ID1 average value equal to 0 for resistive load, for R load. So remaining load, we know that how to find the phi value. So that is phi 1. How to find the phi 1 value. So here RMS value will be the ID1 RMS equal to, so what about ID1 RMS? So it is in between the 0 to 1 by 2 pi into, so 1 by 2 pi into 0 to phi 1 I naught 1 max into sine omega t minus phi, so whole square into d omega t whole power 1 by 2, So similarly, the conduction angle for the diode will be phi. So the conduction angle of the thyristor will be the pi minus phi. So this phi can be evaluated, which we have seen in the starting itself. So how we can find? So for example, if it is resistive load, phi is 0, so the conduction angle of the diode is 0. So the conduction angle of the thyristor will be the phi minus phi 1, so it will be the phi. So let us find fundamental power transferred. So fundamental power transferred will be P naught 1. So is the fundamental power transferred, so which is equal to V naught 1 RMS into I naught 1 RMS into cos phi 1. So this phi 1 will be 0 for the resistive load, so it will be the thing, and this phi 1 will be the pi by 2 in case of the pure inductive load. So we have calculated the phi 1 also. So and this phi 1 we should calculate from this here. So it will be like this. And if you have this summary in mind, so this is sufficient to solve the almost all problems in the full bridge and half bridge inverter.